So today we'll talk about the mechanical properties of fluids. Fluids which comprise both liquids and gases. The distinction of fluids from solids is in that the fluids can flow. That's why their name is fluids. Fluids do not have definite shapes, just like solids. Okay? Solids have a definite shape, but fluids do not have a definite shape. They will take the shape of the container in which they are. We know all these things. These tidbits we know from before. Solids and liquids have almost fixed volume. Gases do not have. Under atmospheric pressure, the pressure of the atmosphere, talk to you about, we say that the volume is a function of pressure. It depends upon pressure. Well, they have very low compressibility, liquids and solids. Compressibility, is the reciprocal of bulk modulus of elasticity, which we learned in the last lecture. So very low compressibility for solids and liquids, which can be said that if there is a change in the value of P, delta P, then the corresponding delta V is very low, very small. Then we can talk about shearing. The shearing stress for the same strain in liquids is much smaller. There is about 1/1,000,000th that of solids. So, and of course, gases have much poor. Now, we'll talk about something we know from before, that is pressure. Pressure, which is defined as the normal force per unit area acting on a surface. That is the force divided by the area. Normally we know that the force is the vector, as also the area is also a vector element. So division, we cannot do that vector force vector divided by force above area vector, because division by a vector is not defined. So instead what we do is the magnitude of the force, which is normal to the surface, divided by the area of the surface, okay, that gives us the average force, pressure. We can also define the pressure in limit delta A tends to 0, delta F upon delta A, like it has been our practice in doing many other things. F is the magnitude of the normal force. So that means if a force is being applied on a surface like this, then it is the normal component which matters, not the total force. Of course, this is what is going to happen. Well, A is also the magnitude of the area vector, and then the dimensional analysis work we make it out. Then P dimension is mLt minus 2, which is force. I always remember this one. divided by L square, so it turns out to be ml minus 1T minus 2. Unit is Newton per meter square, which is also called Pascal. To honor the name of an experimental physicist from France, Blaise Pascal, who was born in 1623 and died in 1662, and merely he had an age of only 39 years. Okay. One of the units of pressure is atmosphere, and this atmosphere is the pressure due to the column of air which stands and at the sea surface. This is equal to 1.013 into 10 to the power of 5 pascals. So after the definition of pressure, we must talk to you about what we call density, okay, and which we know from our childhood days, that the density, which is shown by the letter rho in the Greek letter, is the mass divided by the volume of the body. And I can write this as m upon v, and so from this relation I can write the relation m is equal to rho v and v is equal to m upon rho, if need be, to calculate the volume given the value of the mass and the density, etc. But I insist always that you must write the basic formula from where you can derive it quickly. Density is a positive scalar, okay, and it's this thing is the dimensional formula is ml minus 3 kilogram per meter cube. Okay. Now, one of the most important things is water. Okay. The water of the rivers, and it's different from the seawater. Okay, the water that we take, we drink, etc. The density of the water turns out to be 1000 kilogram per meter cube. It can be written as 1.0 into 10 to the power 3 kilogram per meter cube at a very interesting temperature which is called 4 degrees Celsius. You know, if we cool water down from 100 degrees Celsius to 4 degrees Celsius, then the water, the volume of the water keeps on decreasing. Thereafter, there is an anomalous behavior in water, and that anomalous behavior is that below 4 degrees Celsius, the water starts expanding as you go down to 0 degrees Celsius, when the solidification, that is conversion to ice, begins. Is 277 Kelvin, and the pressure at that time is taken as 1 atmosphere, because we must talk about the pressure and the temperature to know the exact situation, because the things change because of the temperature, and they also so we have a concept of STP or NTP. STP is the standard temperature and pressure, and NTP used to be called normal temperature and pressure in the days when I was a student in your classes. Well, I'll just give you a comparative study of the value of the rho. For water it is 1.00 into 10 to the power 3 kilogram per meter cube. For seawater, it is 1.03. So the density of the seawater is a little more as compared to the density of fresh water. Okay. Then one of our very important friends, particularly in these studies, measurement of pressure, etc., is mercury. Mercury is a metal, but at room temperature and below room temperature also it is liquid. The density is 13.6, very heavy, into 10 to the power 3 kilogram per meter cube. Ethyl alcohol, alcohol, I don't consume alcohol, sometimes medicines only. So that is lighter than water, 0.806. The blood, total blood, that is the red corpuscles and the white corpuscles, everything taken there, is about 1.06 into 10 to the power of 3 kilogram per meter cube. Now air. Air is 1.29 kilogram per meter cube. Oxygen is 1.43 per meter cube. Naturally, because air contains 80% nitrogen and 20% oxygen, so it is vastly heavier. This air is dry air. If it were instead what we can call roughly as wet air, then the value will be much less. Because the water vapor, you can see, for oxygen molecule we have 16 plus 16 is 32. For nitrogen is 14 plus 14, 28. And for water, H2O, it is 18 only. So if the place of a nitrogen or oxygen molecule is taken by a water molecule, vapor molecule, then of course that's lighter in, and therefore its density becomes smaller. And in sound, therefore, there are many things associated with that. Hydrogen, of course, is 0.09 kilogram per meter cube. And as you go away in the interstellar space, is much less. Okay? Now, let's talk about a law, and that is called Pascal's law. Pascal studied the fluids at a length. He had a very wide study of, although he died at the age of 39, Pascal contributed a lot to the study of, and that is why he is honored by giving the unit of pressure as Pascal. It says, it's very simple, is law or principle or whatever you want to say, that the pressure in a fluid at rest. Fluid at rest. The fluid is not moving, the fluid is not in turbulent state, the fluid is at rest. Then the pressure in that fluid is the same at all points that are at the same height or depth. I've just tried to show it to you with the help of this cylindrical thing which is kept horizontal. Its area of cross section is uniform. Okay, this is the left end, and therefore forces are acting on the left side. Forces work normally. So this face, also this face, this is, I'm writing F right, F left and F right, they are equal, areas are equal, so the pressure should also be equal. So the pressure at the left end and the pressure at the right end will be equal. Okay, all over, if this is body and it's immersed in and the area of cross section is not too much, then almost this is at the same height as this one, and therefore all the points will experience the same pressure, which I have tried to show to you. Okay, that I have some points A, B, C on the surface of something which is at the same level, okay, in a fluid, immersed in a fluid, then what we find is that PA is equal to PB is equal to PC. Okay. One more thing. They have to be like that. The pressure got to be equal. There should not be a pressure difference. So that means that under this circumstance, the change in the value of the pressure is equal to 0. If not, if delta P is not equal to 0, then what happens is that a flow results. Okay, and fluids flow from levels of higher pressure to levels of lower pressure, of course. So, with the application of the Pascal's law, we make a calculation and this thing. I've got a water body that could be any other fluid of any other density, but I've just taken a water body, water contained at rest, and I have a cylinder of mass M which is immersed inside. The cylinder has a uniform area of cross section. The distance between the two faces is h, okay, and I call this as level 1 and call this as level 2. So the corresponding pressures are P1 and P2 respectively. The water body has got a density of rho. So now the all the points on this face as also all the points in the lower face, they are at the same level. So Pascal's law applies and it says that the pressure all over this circular cross section over there and all over the circular cross section over here, this pressure is the same all over here and this pressure is the same all over here. Okay. So if you understand this situation, it is very simple that we have a vertical force acting on it which is equal to P2 into A, and there is another vertical force working down, and that is P1 into A. So I can say that P2 into A minus P1 into A will be equal to mg. Okay, because P1 plus mg will be balanced by P2 into A. Right? So I can write P2A minus P1A is equal to mg, and m is equal to rho AH, the area of cross section multiplied by the height of the cylinder and multiplied by G. So A and A are common, and so I get the relation, the difference between P2 and P1, it is equal to rho GH. Rho GH, which is very musical to me, it will become musical to you because we will be using that often, and that is also known as the gauge pressure. Okay? So from this relation, if I take P1 to be the atmospheric pressure PA, okay, at the level over here, the atmospheric pressure is there, and the pressure on the at any depth h is equal to P. For example, I can say that, let us define the levels. This is the upper level, here it is PA, and here it is P, and of course this is H. Okay, so if I substitute these values, take that, then the pressure can be said to be equal to the atmospheric pressure plus rho GH, and P minus PA at the depth H, this turns out to be equal to rho GH, which we call the gauge pressure. Very simple application. The gauge pressure. In the following, I give you an example. If we go out swimming in deep fresh water, and somehow I go to the depth of 10 meters, okay, then the pressure at the depth of 10 meters on the swimmer when we are swimming, that will be equal to, according to this relation, PA plus rho GH, and PA is equal to 1.01 into 10 to the power 5 pascals. For rho GH I can calculate, okay, like this. Rho, the density is 1000 kilogram per meter cube. G is 10 and H is 10. So this becomes equal to 10 to the power of 5. So 10 to the power of 5 Pascal plus 1.01, this is 2.01 Pascal. Okay, almost we can say from 1 to 2 Pascal. So 10 meters column of water is equivalent to the big column of air. The two are equal, and there is a 100% increase. This is very simple to understand. But suppose we are in the deep sea, and seawater is also the density is 1.03 into 10 to the power of 3 kilogram per meter cube. It's not much more than the fresh water, is very close to that. And suppose we go down from the level of the sea, deep into the sea, 1000 meters or 1 kilometer. Okay, that's what exactly happens in the case of submarines. Submarines, they can stay down at the depth of 1000 meters. There could be vegetation, etc. also. Now, if so, and if we work it out, this becomes, H becomes equal to 1000, which means this is 100 into 10 to the power of 5 pascals. Okay. So 1 Pascal is already there due to the atmosphere, and this large amount, 100 pascals, 110 to the power of 5 pascals is due to the column of the water or the submarine. This tremendous amount of pressure. Therefore, the submarines should be designed, the materials chosen should be such that they withstand pressures of that amount. Now I just will wind up this with what is known as the hydrostatic paradox. So as I told you, we are going to talk about hydrostatic paradox, which speaks for itself. There is a kind of a container, okay, I have shown it to you, which has got 3 openings, A, B and C, where the shapes are different. Of course, in this and this the water is more as compared to here, but the levels in all of them are the same, so as also the same level at the bottom of the system. This is called hydrostatic paradox. Okay, need not elaborate more on that. Next, we'll talk about, in the coming lectures, atmospheric pressure and gauge pressure. We'll talk about manometers and barometers, hydraulic machines and hydraulic brakes, etc. Then we go for streamline motion, study the streamline flow, discuss the equation of continuity, turbulence, and then next lectures Bernoulli's principle and this and that and that. So things are going to be very interesting. They are in the case of fluid dynamics, and I hope I enjoy being with you during these lectures. So for today, once again, our motto, UQVA, okay, and do write in the comments section if you need something more, or if you are not able to understand something. I'll be glad to listen to you and to make myself available to answer those questions. Thank you very much.